Okay. All right, so let's get started. Welcome to lecture 38. I think it is. I gotta, let's see. Try this. Yeah. All right, so lecture 38 is a little bit of a hybrid lecture. We're going to finish up talking about networks, and we're going to talk about disks very quickly, which is okay because disks are slowly going away. So, but that doesn't mean you don't have to know about them for the final. Okay, so you guys need to quiet down a little so we can get going. So 61C in the news. You got to love this one since we're talking about networking today. So this came out before Black Friday, and it's a couple malls that are basically using your cell phone to track where you go in the mall and how long you spend in a certain place. And you might be nervous about that because maybe you feel like it violates your privacy, but it's okay. You can opt out. All you have to do is turn off your phone. And in a couple places, they even put up signs that told you that they were doing it and that you could turn off your phone. So, kind of a crazy story. What's happening here is actually pretty interesting. Can you guys calm down? So what's happening here, if you think about it, the online retailers have a real advantage, right? Because when you're searching through a site, they have a cookie on your browser. They can track what pages you look at. They can guess how long you spend looking at each page. They can figure out all that stuff. They can figure your path through their site. They can even, if they make agreements with the right people, figure out your path through their site and other sites. But traditionally, brick and mortar stores don't have that advantage. So they have much less information about their customers. So this is brick and mortar stores' way of trying to level the playing field in a way. It's kind of interesting. So we'll see how, as people start understanding more and more that this is going on, and notice this isn't the GPS or anything like this, right? This is just them, seeing where your phone is in the mall. It's a little, there's really not much you can do for that except for turning your phone off. So something to think about. Of course, none of you guys went shopping on Friday because you're all busy working on projects. So, all right. So let's get to the topic of today. Here's where we were last time. We talked about exceptions and interrupts. And in particular, we talked about interrupts as a way to handle dealing with I/O devices. Networks are another form of I/O. And we talked about two kind of important levels of the network. We talked about the internet. Well, you guys are really talkative today. So yeah, thanks. So, and then we talked about this thing called the World Wide Web, which has only been around, believe it or not, like 15 years, right? Am I doing my math right? No, 25 years. But still, time flies. It's hard to believe it wasn't always around. And then we talked a little bit about shared versus switched networks. So what I want to do now is finish this just very high-level discussion of networking. And then, of course, we have entire classes on networking, which we'll tell you about. And then I'm going to tell you a little bit about, we'll talk a little about disks and RAID. So what we're trying to do is we're going to build a network of these switches. And we're going to do what's called routing. So if I have a message in this computer and I need to send it to this computer, I'll package it up. I'll have a source address and a destination address. And then I'll just inject it into the network, and by these switches doing the right thing, the message will eventually get to the computer it's trying to get to. Okay, and so in order to make that work, you have to have a way of talking about endpoints, right? You need some notion of an address. You need some notion of a unit of information that you're going to send. And then you need a bunch of different protocols, which is what we're going to talk about next. All right? And these protocols are a way of, they're a type of abstraction. Right. So I showed this slide last time. So here's where we were last time. What you're going to do is you've got some data that you're going to send, right? Maybe it's some text that's part of a web page. Maybe it's a command that you want to send to a remote site. Maybe it's an email or whatever. And that's going to get wrapped with some meta information, basically a header which tells you where the message came from and where's it going to, how long it is, some additional information for the protocol to use. This is an acknowledgement. And then a checksum, okay? And the checksum is there for you to be able to detect if certain parts of the message have been corrupted. Now, so let's take a look at how this is going to work. So on the sender side, right, it all starts at the application level. The application decides it's going to send a message. It copies the data to some area in the operating system, right? And then it basically hands the data to the operating system and says, please send this message, okay, to this location. Now, the OS calculates this checksum, and it initializes a timer, okay? And then the operating system hands over the data to the network interface, which is actually typically a piece of hardware, often a network card, and then says, go ahead, start the timer and send the message, okay? So at a high level, that's what's happening on the sender side. Now, last time we talked a little bit about what this checksum is, and I followed up with my friends who do networking for a living. And it turns out that for typical protocols, like we'll talk about TCP in a second, what actually the checksum gets computed not over the data, but over the header information. So somebody asked last time, what happens if the source or the source ID in particular gets corrupted? And the answer, well, I'll show you in a second. So the answer is this is what happens on the receiver side. So you notice it's going to go backwards. So we went down the stack, and on the receiver side, we're going to come up the other way. So the OS gets the data from the network interface and copies it into a buffer. It calculates the checksum, and then checks it to see if it matches the one that came in on the message. Okay? Now, TCP is going to do the checksum not on the data, but actually on this metadata. So if for some reason the source or the destination or anything else in this header got corrupted, then the operating system or the messaging layer of it will be able to detect that there's a corruption, and basically it'll just delete the message. Okay, so it won't pass it to anyone. It won't try to return to the sender because remember the sender might have been corrupted. Okay, so it just says, oh, okay, there's something wrong with this message. I'm going to throw it away. Okay, and then it's going to depend on a higher level protocol to do the right thing. Okay, if the message does check out, right, so nothing was corrupted, then it sends an acknowledgement back to the sender and then copies the data, basically returns up to the application, puts the data into the user's address space, and then tells the application, okay, go ahead, you've got data there now. Okay, so that's going to be done with interrupts the way we talked about last time. Okay, so from the operating system down through the hardware on the sender side, and then in the reverse direction on the receiver side. Yeah?
What happens if the checksum gets corrupted?
Right, so good question is the checksum's part of the message. What happens if that gets corrupted? And the answer is the system recognizes it as a corrupted message and basically just swallows it. So that's a little bit of a problem with checksums is you're sending extra data. That extra data can get corrupted, and if it does, you can't tell. If the checksum doesn't match the header, you can't tell who's wrong. So you just have to say, there's a problem with this message, please resend it. Okay, and the way you say please resend it is by not acknowledging. Okay? All right. So that's at a very high level. Let's go just slightly deeper, although, as I say, there's an entire semester-long class and an entire field on this type of stuff. So we're only going to touch, sort of scratch the surface. But, basically, the networking stack, or the software and the hardware underneath it, is going to be organized as a hierarchy of layers, right? So we have this great quote from Shrek about onions and layers. And, at the high level, you've got some application. Maybe it's an email system. Maybe it's a chat server. Maybe it's some sort of a game you're playing, whatever. But an application that's sending messages from some instance of the application over here to some other instance of the application over here. Below that, you have a transport layer. Below that, you have a lower level that's doing just network transfers. And then below that, you've got physical links, okay? And if you're familiar with networking, there's actually a 7-level stack that's defined called the ISO stack. But typically, these are the 4 levels you're going to find. It's rare to find all 7 levels being used. So what we're going to have is, at each of those levels, is we're going to have a communication protocol. And the trick we're going to play, it's very cool. Each level is only going to think that it's talking to its partner at the same level on a different machine. So if you're an application, you don't worry about all those things, the physical layer and the transport and all that. Okay? You just worry about talking to the same application over on a different server. Okay? And we're going to do that at every level. And so each level thinks it's talking peer-to-peer. It's talking to a process at the same level. But of course, each of those levels is implemented down below by a lower level protocol, okay, until you get down to that physical level. So that's sometimes called encapsulation, that we're going to carry high-level information in a lower-level envelope. Okay, and I'll show you what that looks like in a second. And then also, you might not want to worry about the physical limitations of your network. So, for example, certain networks only send small chunks of data at a time. If you wanted to send a large amount of data, like, say, a big web page, you don't want to worry, if you're a web server, you don't want to worry about splitting that into whatever physical chunks the lower level needs. Okay? So you send, a big chunk of data, and the lower level fragments it into the sizes that it can deal with, and then reassembles it on the other side. Okay? So let's see some examples of that. So let's say I've got 2 applications that want to talk to each other. So this application is going to send a message to this other application. Okay? And that code is basically written as if that's happening. Okay? So if I'm going to send an email, I'm going to send that email, to your email client. All right. But at a lower level, what's happening is that message is getting translated into something at the next lower level. So now we attach the envelope. So we have a header and a trailer. Okay? And at that level of the system, the protocol is written as if it's going to transfer to its peer on the other server, right? So that's a peer-to-peer transfer. But that's not really what's happening. Okay? No message has been sent yet. Then we go down further. Okay? So let's say we go down to that lowest level. Okay? And we put another envelope around that message for that lower level. So we have our application. We have an envelope for the next lower level, and then we put that in an envelope for the lower level of that. And then the bits actually get transferred. Okay, once they get to the other side, we pull off, we check the checksums, pull out the message. We're still not done, so we check the checksums here if we need to. We pull out the message, and then we return it to the application. So the key abstraction here, and abstraction is the important word, okay, is that at each level, you think you're talking to somebody on the other server who's exactly at your level. But really what's happening is it's getting translated down the stack to the lowest layer, the bits get sent across the wire, and then it gets translated on the way back out. Okay? But the nice thing about this is, if you're writing your application up here, you don't really have to worry about the details of those lower level protocols. So you don't know if the message is going over a wireless or a wired or a switch or a shared network or whatever. Okay? Or 2 cans, tied together with a piece of string. You don't have to worry about that. Okay? And that's the important part of abstraction. So let's look at a particular stack. And we'll look at not just any old stack, but we'll look at sort of the most important one, which is a TCP/IP stack. So TCP is the Transmission Control Protocol, and that runs on top of IP, which is Internet Protocol. And TCP is basically the foundation of the Internet. So when you send messages across the Internet, particularly if you're doing anything on web pages or most application level things, it's done over TCP. And the reason is that the Internet Protocol, that one protocol lower, is what's called a best effort protocol. And best effort is kind of a euphemism. Okay, it's a term that networking people use to make themselves feel better. But best effort means, you're going to send a message over IP. It might get there. It might not get there. Okay, no guarantees. Okay, so it's really hard to write an application directly on top of IP because you just can't trust it. You would have to check, did the message get there? How long do you have to wait until you get an acknowledgement? If you haven't gotten an acknowledgement in a certain amount of time, you resend the message, but then wait a minute, maybe the message really did get there, now it's there twice. You have to worry about all that stuff. You don't want to worry about that. So TCP worries about that for you. So TCP is built on top of this unreliable protocol. It's a really cool thing. You build a reliable protocol on top of an unreliable one. Okay, and so TCP guarantees delivery, and it also guarantees order. Okay, so if you send a bunch of messages out in TCP, the TCP protocol on the other side will rearrange the messages even if they come in some random order, right? Because remember, they might take very different paths through the network. It'll rearrange them and then return them in order. Okay, so TCP gives you this very strong set of guarantees that you can write your applications against. Okay, but it's done on this very efficient, very lightweight protocol, which is IP. Okay, and when we talked about the internet being invented in 1962, that was IP. Okay, and then it was only 6 or 7 years later when people got frustrated trying to actually use IP that TCP was developed. Okay, and it's because it was so hard. It was so hard to get right. So TCP/IP is kind of the language that most network devices speak these days. It's becoming more and more popular, and it's so popular that even in a simple local area network, you tend to use TCP just because it works and it's pretty efficient. Okay, so what does TCP/IP look like? Okay, so let's say you have an application that's going to send a message. So, okay, great, here's the message. You hand it over to the operating system. You say, hey, I want to send this TCP message. Or I want to send this message via TCP. So it says, great. TCP takes it and says, okay, I'm going to turn that into a TCP message. And the way I'm going to do that is I'm going to put in by TCP header, and I believe there's also a trailer. Okay, so it basically puts the message in this TCP envelope. Okay, so we just went down one level in that picture. And TCP is going to think that it's going to send it to a TCP connection on another machine. Okay, your application, of course, thinks it's sending it to an application on another machine. All right, TCP, though, isn't at that lowest level, so it's going to implement its functionality through IP. So IP also adds its own headers, and you end up with something like that. Okay, so you have the data inside a TCP envelope inside an IP envelope. Okay, but we're still not done yet because IP isn't that lowest physical layer. So we got to go one more layer. So a typical layer that you'll find is something like Ethernet, okay, which is what we tend to run around here. And Ethernet has an interesting restriction. In Ethernet, the biggest packet you can send is 1,500 bytes. Okay, so remember when you created this message, you didn't worry about how long it was. You didn't worry about splitting it into little pieces. But Ethernet can only send things in 1,500 byte chunks. So the Ethernet protocol, right, which is running in the hardware, is basically going to split that thing into a series of Ethernet packets and send those out. Okay? And then it's going to be up to the receiver on the other side to collect all those packets, piece them together in the right order, and return them ultimately to the application. And of course, if any packet gets corrupted or lost along the way, the protocol has to resend it. Yeah? Why wouldn't TCP and IP break them up so they fit into Ethernet chunks?
Well, break up why wouldn't TCP break up the message so that it fits the TCP?
Okay, so why wouldn't TCP break up the message itself? Well, the idea there is that you want to be able to have the TCP layer work basically for any underlying protocol. So different underlying protocols have different size restrictions. And so it basically says, hey, Ethernet protocol, I want to send this chunk. And Ethernet says, well, geez, I have to do it in 1,500 byte chunks. But if you gave it to some other low-level protocol, it might not have that restriction. Yeah. So it's all about sort of what abstractions, what details are being hidden at every layer. Yeah, in the back there. I'll get you next. Yeah, go ahead. Yeah, go ahead. Okay, good question. So does it have to resend only the packets that don't make it, or does it have to resend the whole thing? Oh boy. I think, yeah, so the ACK happens at the TCP level. So it'll end up having to send that whole thing again, I believe. Right? Because there aren't necessarily any acknowledgments at the Ethernet level or at the IP level. Remember, IP doesn't guarantee delivery. So, so I think in this case, you would have to send that whole message again. Was there, yeah, question here?
Kind of hard to tell the diagram.
Yeah, sorry.
Does it split? One package has both the headers and no data, or does it look at the headers and the data together split evenly such that the first package has headers and data?
Yeah, so good. So, yeah, this picture's a little ugly, I'm sorry. It's probably been passed down over the years from, oh, maybe Dan wrote it, I don't know. Yeah, from a while ago. Basically, Ethernet doesn't care what the bytes are. It just breaks it into 1,500 byte chunks. So it doesn't care whether it's header or data or a combination of header and data. And again, that's part of the abstraction. It'll get pieced together by the higher layer. Yeah?
What mechanism does TCP use to guarantee?
Oh boy, good. That's a really good question. So what mechanism does TCP use to guarantee the delivery? So that's it's a short question with a long answer. But the basic idea is that it basically keeps track of messages when they get sent, get a sequence number, and it keeps track of acknowledgments of each of those sequence numbers, and for things and so it can tell if if it got message 3 and message 5, but didn't. After some time, it realizes it didn't get message 4, so it asks for message 4 to be resent. And then there's this whole protocol on sort of how often it asks. And there's this sort of back-off that you do over time, that you don't keep asking. If you don't get it, you wait a little while longer, and then you ask again. But it's a fairly sophisticated protocol that's covered in a lot of detail in CS122. So we're just given sort of the baby version of it here. But it's just acknowledgments and counters and retries is kind of the basic idea. Yeah?
On the other hand of the internet, how does it know how to put the packets back together? How does it know which comes from where?
Yeah, how does it know what to put where? Well, again, the packets can be tagged with sequence numbers. So you can put sequence numbers, you can order them by the sequence number. Is basically how it works. So, okay, one more question, and then otherwise we'll end up having to do CS122. Yeah? Ethernet, okay, so let me start from the parts that I know. TCP has its own checksum. IP adds its own checksum. I don't know if Ethernet has its own checksum or not. Do you know? We don't know. So that's something we'll have to look in Wikipedia for. But TCP and IP each put their own checksums on it for sure. And I'm not quite so sure about Ethernet. And this is a much longer discussion, but in networking there's this concept of what's called the end-to-end argument, which is ultimately what really matters is that application-to-application communication. So if you're doing checking at that level, that relieves you from having to do certain types of checks at the very lowest levels. So, so that's why, for sure, the higher levels do it. I'm not sure if the lower levels do it. The problem with computing checksums is it takes time. And if you're trying to pump data through a network at 10 gigabits a second or something, you don't want to have to be doing a lot of checksum addition and checking. Okay, one more. Yeah.
The higher up you have this checksum thing, you have to resend more data.
Yep. So the comment is a really good one, which is the higher up you detect the problem, doesn't that mean that you have to resend more data potentially? And the answer is yes, but you've got to remember the fundamental principle here is that if errors are rare, then the common case is that there's no problem. So you want to make the common case go fast. So you don't want to slow down every single Ethernet packet if if the vast majority of them are getting through okay. And so that means in those rare cases when you do detect a problem, you might end up resending more. But overall, you're going to win because most of the time there isn't a problem and it goes much faster. So that's the trade-off, though. But you're absolutely right. The higher up the stack where you check a problem, where you detect a problem, potentially the more work you're going to have to redo to fix it. Absolutely. So good. So it's obviously a deep area and a deep set of issues. And it's amazing, that networks work as reliably as they do. And again, it is the topic of a whole class. So the idea here was just to give you a little bit of a teaser on the basic idea. And the key insight here for this class is this idea of abstraction, that each layer thinks it's talking to a counterpart at the same layer on the different machine, and the details are handled subsequently, lower and lower in the stack. But each layer thinks it's talking to somebody at the same layer. That's the fundamental concept that we want to get across. Okay? All right. So I want to do maybe even a quicker tour of the idea of disks, because even today, disks are really where most of our data ends up being stored. So, and this is really just to round out our discussion of I/O devices. So, disk is, I'll show you a picture in a second, but it's a really kind of primitive technology in a way. It's very physical. There's a lot of moving parts. It's, on your computer, basically you have a fan and the disk are the only moving parts. And if you have a new, even some laptops now don't even have mechanical disks anymore. So now you just have a fan. But so it's information is stored magnetically. And what's cool about disks is there's two things that are important about disks. One is that they're relatively cheap per byte. So you can store a lot of data in them for not much money compared to something like main memory or even flash that we'll talk about. And the second part is that they're non-volatile. So if the power goes out, you don't lose data. Whereas for DRAM, if the power goes out, when the power comes back on, you can't trust what's in the DRAM anymore. Okay? So it's cheap per byte, and it's non-volatile. That's why disks are important. It says that there are two types, floppy disks and hard disks. I'm not sure you can get floppy disks anymore. So we'll just talk about hard disks. Basically, they're used in a computer system for two things. One is long-term storage, right, because it's cheap per byte. And then the other is as swap space for main memory, okay, which is what we talked about when we covered virtual memory. But again, you want to be able to run your application mostly in memory, right? So you'll fault it in, but you don't want to have to keep going back and forth to that disk because that disk is effectively on Jupiter or Pluto, depending on your attitude about those things. Okay, so but that's why we use them. Okay, perfect. And here's the picture. I hope you can see it back there. If you've ever seen a record turntable, you know how a disk works, more or less. It's a little slightly different, but you got these platters that spin around, and they spin at 5,600 rotations a minute or 7,200 rotations a minute. There's this arm. Oh, there's probably some stuff here. There's this arm assembly, this actuator, that basically moves back and forth across the disk. Okay? And that's called a disk seek. All right, so at the end of the arm is this read-write head. So what happens is this thing's spinning around, right? It's got this magnetic, this ferrite surface on it. And as the surface goes under that read-write head, it can pick up which bits are set and which bits aren't set. Okay, and furthermore, it can set them and unset them. Okay, that's the reading and writing part. So if you want to read some data that's over here, what do you have to do? Well, you move that whole arm assembly back here, right? That's a physical, that thing actually is at a dead stop. It accelerates, it cruises, it decelerates. I mean, this is really how these things work. It gets to the right spot on the disk, and then it waits for the right part of that disk to come under the read-write head, and then it starts transferring the data from that head, back here through the controller and out to memory. Okay, so it's really, really primitive. It's hard to believe that all you guys with your fancy MacBook Pros there and other laptops, that's what you've got running in there. Okay. Just some other terminology. Yeah, typically you stack up the platters, and there'll be a read-write head in between each set of platters. And sometimes you'll have a read-write head on either side of that arm, so you can read the bottom of the top one or the top of the bottom one. Okay? So here's an artist's rendition of that same thing. And let me just tell you a little more terminology. So a surface is called a platter. Okay? The platter has these concentric rings that are called tracks. So you have inner tracks and outer tracks, right? And a piece of a track is what's called a sector. So when you have a page of a file or a page of memory, and you write that out to that disk, a combination of the operating system and the disk controller are going to map that page onto its physical locations, okay? And typically a page will be made up of multiple sectors. And it'll try to put those sectors near each other, but sometimes there's impurities on the disk and so on that it has to move things around. But again, it's all virtualized. You don't really have to worry about it. When you say, write this 4K bytes to the disk, you just say write and it goes and does it, and you don't actually necessarily know exactly where they are on the disk, okay? But basically, in order to read the disk, think about what you have to do, right? You have to move the arm, that's called the seek time. You have to wait for the disk to spin around, that's called the rotational delay. And then you have to transfer the bits off of that platter, out through the electronics, okay? So those are the three components that make up the cost of a disk read, okay? So that's why when you're doing random I/O, right, when you're doing random access to a disk, it's going to take you 10 or 20 milliseconds to do it, all right? Because you've got to move, typically you've got to move that whole ARM assembly and wait for all that stuff to happen. Whereas sequential access is typically going to be a lot faster because you move the ARM once, and then you start reading the data. And you can read more and more, and if the controller did a good job of putting sequential stuff near each other on the disk, you won't have to move the heads and seek and wait for things to spin around and everything. So that's why sequential access on a magnetic disk, on a hard drive, is much, much, much faster than random access. Okay? Yeah? Right. So there are thousands of tracks on each platter, and we only drew 2 because we were lazy, but you're right. So tracks get bigger as they are closer to the edge of the disk, so outer tracks are bigger than inner tracks. And it's only relatively recently that people started figuring out how to put more data in the outer tracks than in the inner tracks. It used to be you'd put the same amount of data in each track, but now most disks are smart enough to pack, they pack the bits at the same amount, so as you move out to the disk, tracks actually have more sectors in them. So sectors typically a single fixed size, and then you have more sectors per track as you move out. Yeah? Okay, that's a really great question. So the question was, it's up to the file system where you put files on the disk. And the answer is sort of. So the disk has, didn't really show it here, but the disk has its own processor and actually some local memory, which is called the disk controller and the disk cache. And that controller is actually what knows which bits are stored in the disk. And so basically when you tell the operating system, or when the operating system says, hey, store this file, out on this disk, it's basically a hint to the controller that stuff should be stored sequentially. But the controller doesn't have to store it that way. And so so the answer is you have some control over where things get put on the disk, but it's not direct, and sometimes the disk will fool you. It'll put things in a different place than you thought it was going to. And it's, again, just that level of abstraction. One of the reasons that happens is because, as I said, sometimes a sector will go bad, right? And you can't write to it, so you just don't have the option of putting things there. So the controller will put that data for that sector somewhere else. Also, you have the same problem, just like when we talk about in the networking, where, you know, a higher level protocol might work over multiple different physical protocols. Same thing here, right? Your operating system is going to work with lots of different types of storage devices. You don't want your operating system to have to worry about the geometry of every single device it has to talk to. So, you know, basically what the operating system does is it gives hints of where it would like things to be, and then it's up to the disk smarts, the controller, to try to, you know, uphold those hints as much as it can. Yeah? How does the file system come into play? So the file system is basically part of the OS. It's the part of the OS that knows, that deals with this abstraction of files, which is a sequence of pages. And yeah, it basically, when you say to read a file, it knows how to translate that into a series of requests for pages from the disk. And same for writing. So it's kind of a lower level of the operating system. Yeah?
So would the track that a program is on actually affect how long it takes to read it from disk? Since maybe if it's closer to the center, it'll get broken
Yep.
into different...
Yep. So, so the question was, you know, does the track that a program or even a piece of data is stored on, you know, matter for the performance? And the answer is yes, it does. And so a lot of systems will let you define regions of the disks, so that you can. So for example, some systems will let you define a swap space, and that swap space, you know, the idea is that swap space will be on one part of the disk, so that if your virtual memory system is reading and writing stuff, it'll, you know, do it in this local area, as opposed to having to scan all the way, you know, across the disk. Because remember, you're physically moving that arm. The further you have to move it, the longer it takes. And so, yeah, so placement of data on these drives is really important. The problem is, because of the complexity of the system, you only have limited control. So you can basically say, you know, here's a region of the disk that you should put this in. You know, here's a bunch of stuff that I'd like you to store sequentially. And, you know, you don't actually know what the disk is going to do. It's a little, it's kind of interesting. Okay? It's just like in a modern car, when you step on the accelerator, you know, it used to, it used to be that there was a little thing connected to a lever that was coming from your pedal that, you know, kind of moved the carburetor this way, right? It doesn't happen anymore. Right? You step on the pedal and, you know, this series of electrical signals get sent and all this other stuff happens. And, you know, you hope that it ends up doing what you want it to do, which is make the car go faster. It's kind of what's happening here. Okay? All right, so those are disks. And, you know, as we already talked about, there's newer technologies coming out. Flash is one. Flash has the advantage. So disks are this crazy anachronism, right? They're these moving parts sitting in your beautiful, brand new laptops. You have this motor that's spinning around and this arm that's moving back and forth. It's really amazing. Flash says, okay, that seems a little retro. Why don't we use solid state to store stuff? And so Flash is non-volatile memory that doesn't have moving parts. Okay? And so Flash has some advantages, namely it doesn't have moving parts. And so, you know, if you drop a machine with Flash in it, like I did with mine recently, so far, knock on wood, it seems to be okay. Whereas if you had a spinning disk, and that head crashes into that magnetic surface, that's bad. So, you know, you solve problems like that. And, you know, it's better for power. It's not going to, you know, you don't have moving parts that are going to wear out and so on. The problem is, though, there's two problems. One is it's per byte more expensive currently than magnetic disk. All right, so that's an issue. And the other is that there are some limitations in Flash in terms of how many times you can write the same location. Okay, and so, you know, those are called erase cycles. And, you know, array cycles are going to be somewhere between, 100K and a million times that you can actually write a location. So the controllers for Flash devices, this is a picture of a disk that's made up out of Flash. The controllers for Flash devices, they don't have to worry about optimizing for seek time and things like that, but they do have to worry about what's called wear leveling, which is you don't want to keep writing the same location, because if you do, it'll wear out. And so a big part of what Flash controllers are doing is spreading the data around the device in a way that you don't keep, in a way that the whole device kind of ages at the same rate. that you don't have parts of it burn out. Yeah. I don't think the same thing happens for hard drives. I've never heard anyone, I can imagine, I don't think so. I've never heard that raised as an issue. Yeah.
But don't people say that like all hard drives have a lifetime?
Okay, well that's a different question. So the question was, don't people say that hard drives have a lifetime? And they do. We'll talk about that in a second. The reason they have a lifetime is because they've got these moving parts. And so it's not that the surface wears out, it's that the moving parts break. Okay? So, I don't want to talk too much about flash, just to say, if you look at sort of one set of products, so here's some iPods, and this is just slightly updated version of what's in there. So, the Shuffle and the Nano and the Touch all have flash. Interestingly, the Classic has a moving disk in it, right? And you can tell when you pick it up, it's heavy. So that's just to show you sort of that this stuff is slowly making in. And then, if you have one of these, like a MacBook Air, this is all flash. There's no hard disk in this thing anymore. So that's pretty recent. And, again, as the cost of these flash devices come down, you'll see them more and more. Hard drives will become used in, more and more specialized applications. Okay, so, but this gets exactly to the question that was just raised, which is, well, I'm going to jump ahead a little bit, but don't disks wear out? Okay, so there was another thing going on, and this is actually some work that was done here at Berkeley. So in the late '80s, Dave Patterson and Randy Katz, who often teach this class, basically had this question. They said, okay, we have these really low-end cheap disks that are these 3.5-inch diameter disks, but our servers are using these monster disk drives that are 10 inches or 14 inches or so on. And the question they asked was pretty simple. They said, okay, if you think about how disks work, right, one of the main costs is moving that arm, okay? And so if you had a bunch of these guys, instead of one of those guys, you would get that many more disk arms. And then you could have those arms all moving in parallel, right? That's the name of the game we play here. So if you had more disk arms, you could have them moving in parallel. You could get the disk to be much faster. So you get much more bandwidth out of the disk. Okay? So the idea then was to say, okay, how many of these 3.5-inch disks could I put in the equivalent size of one of these big disks? Right? So it's called a disk array. I'm going to put 4 of these guys in the same size so I could put one of those guys. Okay? So that's the idea of a disk array. So if you do a back-of-the-envelope calculation, this was again around 1988 at the time these guys were doing it, they said, okay, I've got two choices. I've got my mainframe type of disk, which is big at the time, 20 gigabytes, right, 1988, right, and it's got these properties. It's 97 cubic feet, right, so I don't know, what's that, a refrigerator? And then you've got this 3.5-inch drive that only holds 320 megabytes, okay, and it takes up 0.1 cubic feet, and here's some other statistics, okay, and then you say, okay, great. If I wanted to get the equivalent capacity of my big drive by using a bunch of little drives, how many would I need? And the answer is about 70, a little less than 70, but let's say 70. So now what I want to compare is 70 of these little guys to one of those big guys. And if you do that, you find out some interesting things. So you find out the capacity is roughly the same, 23 versus 20 gigabytes, but the size is a factor of 9 smaller. The power is less. The data rate is much faster, right? 15 megabytes a second here versus 120 megabytes a second here. The I.O. rate, the number of IOPS, the number of I.O. operations you can do per second, is a factor of 6. And it looks like a big win, and it's cheaper, and it's great. Okay, so that's the idea: is that it's for less money, less space, you get the same capacity, and it's faster. Okay, and so on the surface, it looks like a good idea, except there's one little problem, and that's this one right here. Right, that's the mean time to failure. Okay, so one of these big disks could run 250,000 hours in between failures on average. Okay, so you buy the thing, it runs for 250,000 hours before it crashes. Okay, these smaller ones were still pretty good, not as good as these, but 50,000 hours before they would crash. Okay? But now the problem is, when you have 70 of them, what does that do to your mean time to failure? Okay? And so here's the way to think about it. The reliability of n disks, assuming that they fail independently, is basically the same as the reliability of one disk divided by n. Okay? So if your mean time to failure for one of those little disks is 50,000 hours, right? That's how often it runs on average before it crashes. But if you have 70 of them, that means on average, every 700 hours, you're going to have a disk failure. Okay? So your mean time to data loss, or to not being able to get at some of your data, goes from what used to be 6 years down to 1 month. Okay? Now, granted, you only lose 1/70th of the data, but still, that's data loss, and chances are the data you're going to want is on that disk, right? So, so the problem with these things is reliability. And if you just took a bunch of disks and did what we said before, which is collect them and then you try to treat them as if they were one big disk, it would be too unreliable to be useful. So the idea was then to say, okay, let's try to be a little smart. Let's use redundancy to try to solve this problem. Okay? So just like when we wanted messages to be more reliable, we added some redundant information, which was a checksum. Same thing here. For the disk to be more reliable, we're going to store some redundant information so that we can tolerate some failures. Okay? So this was a project called RAID, Redundant Array of Inexpensive Disks. And this is a picture of the first RAID system. It's called RAID the First. That was developed, I think, actually in Soda Hall. So that was the first RAID thing. And now it's a multi-billion-dollar business, tens of billions of dollars. Okay? And when they defined the RAID concept, they defined a couple levels, or a number of levels, actually 6, I believe. So let me just tell you quickly what those are. RAID 0 is no redundancy. So if I have 4 disks, I just store everything on those disks once. So I have A here, then B here, then C here, D there, and so on. And that's that case we're talking about, right? That's where you're going to get a mean time to failure. If you had 70 disks, you'd get a mean time to failure of about a month. Okay? It has the advantage, so it's got bad reliability, but it's got the advantage that it's faster because in this case, if you have 4 disks, you can get 4 reads, 4 IOs going at the same time. So it's going to be 4 times faster. Of course, yeah, okay. So RAID 1 says, okay, well, what I'm going to do is I'm just going to mirror the data. Okay, so I'm going to have double the number of disks. I'm going to have an exact copy of each disk. So here's a disk with A, B, C, and D on it, and I've got a mirror for that. And here's my disk, another disk, I've got a mirror for that. Okay? And RAID 1 is going to let us tolerate pretty much any single disk failure, right? If this disk fails, that's okay. I can still get the data from this disk. Okay? And it's got some advantages in terms of performance because I can, read and write a bunch of things in parallel. Now, writes get a little more expensive because when I go to write, say, item B, I've got to do 2 disk writes instead of 1. Okay? And the cost of the disk is now doubled. Okay, we'll cover it after, okay? But that's what mirroring is. So you double the number of disks, that doubles the cost. It doubles the amount of work you have to do when you do a write, but it gives you fault tolerance, right? Now you can tolerate any single disk failure. All right? Level 2 we're going to skip. Level 3 starts to get more interesting. It says, okay, we can actually do something smarter than full mirroring, which is we can do parity. Okay? So remember, parity is when you basically count up all the bits and you decide are the bits even or odd, right? It's a number of ones, even or odd. Okay? And so what you do here is you stripe this thing so each byte, if you have a sequence of bytes, you'll put byte 0 here, byte 1 here, byte 2 here, byte 3 here, and so on. Okay, and you'll just round robin those. And then for each stripe, you'll put the parity for that byte on this separate disk called a parity disk. Okay? Now, that's got an advantage. Now, if any disk fails, right, the system still works. Oh, well, that's how many drive failures can be tolerated. The answer is 1, right? Because if this disk fails, you can recreate that data by taking this data, this data, this data, and the parity for that stripe. And you'll know whether the missing bits were ones or zeros by doing that. Okay, so this redundant information here is giving you better reliability. But instead of having to double the cost of your disks, like we did in the previous case for RAID 1, here we only have a 25% increase, right? Because we've got 4 original disks, and then we add a new one for parity. Okay? Sorry, let me just get through, and I'll catch you after class. Okay? So this one has the advantage that it can tolerate a single disk failure. It only costs 25% more than the original. And it's also got the advantage that you can read the data in parallel, so reads can be really fast. But there's a problem with this one, which is every write that you do now has to write not only the disk where the data is, but it also has to go to the parity disk. So that parity disk is going to see 4 times the write workload of any of the individual disks. Okay? But it's a pretty cute technique. RAID 4 takes that technique and it says, okay, instead of doing it by byte, I'm going to do it by block. So I'm going to have these big blocks of data, and then I'll have parity blocks over here. Okay? And what that does is now I don't have to have my disks all spinning together. I can, if I want to read a big chunk, I just read it from this disk, and so on. Whereas the other one, if I wanted to read a big chunk, I had to read it from all the disks because the bytes are spread across these drives. So that's 3. That's 4. The problem with 4, though, is that this parity disk is still a bottleneck. And so what 5 does, and this is the last one I'm going to talk about, is it takes that same exact approach. It has block-level parities, but what it does is it spreads them across the disk. So you can see the parity for stripe 0 is on this disk, for stripe 1 is on this disk, for stripe 2 is on this disk, and so on. So what that means is you're spreading that load for writing the parity across all those disks. So you don't have a single disk that's a bottleneck anymore. Okay? Now you still have the problem that if you want to do a write, you have to write multiple disks, but at least you've now spread the load out. Okay? So that was just a quick overview of RAID, but the important thing is that you want to go to multiple disks because they're cheaper, they're smaller, they use less power, and you get much better performance because you can get parallelism. But when you do that, you have an availability problem because more disks means more failures. So you have to do something to address that, and the way you address it is with these different types of redundancy. Okay? So with that, I'll let you guys go. When we meet next time, we're going to hear about large-scale computing, and then we're almost done. All right?